Hello, welcome to today's video. Today we're looking at the modulus and argument of a complex number, looking at how to calculate them, but also explaining what they are. But we'll look in a future video why we care about them. So let's get going. So first of all, what is the modulus of a complex number? Well, it's actually fairly simple and it has a very strong link to other areas of maths. Like for instance, if you've done vectors in pure maths, the pure maths aspect of maths A level, but also you've come across this term modulus before, again potentially in the maths A level syllabus earlier as well. But if you haven't, don't worry, something to look forward to future. So what does it mean? Well, first of all, notation. This is why we call it the modulus, because we use the modulus brackets, and modulus brackets are basically straight line brackets that go either side of something. So if we want to find the modulus of z, we put straight line brackets around it to denote that. But also you can do that around the complex number itself. So if you find the modulus of, I don't know, let's say 4 plus 6i, then you would put straight line brackets around it like that. What does it actually mean though? Well, if you're on an Argand diagram, and so put my labels on the axis to make that clear. Of course, a complex number is something that can be plotted on here. Its real component decides how far left and right it is and how far up and down it is. If you need a reminder of what an Argand diagram is, go watch my video on them. So if we have a complex number, let's say up here, of course, something we often do with Argand diagrams as well is draw a line linking that point to what we would have called the origin before, but now it's just the point, the number I should say, 0, when we're on an Argand diagram. What the modulus of that complex number is effectively just the length of that line I've just drawn. So we're talking about that length there. So working that out is actually quite easy. Let's say this was the number 4 plus 6i. Of course, there would be a length here decided by its real component, and then there would be, if we form a right angle triangle, there would be a length here formed by or decided by whatever its imaginary component was. And of course, then all we need to do is find the length of that diagonal side, which we know very well by this stage would just be found using Pythagoras. So therefore, in general, we can say that the modulus of z, a complex number z, if that complex number z was equal to a plus bi, then the modulus of z would be equal to the square root of a squared plus b squared, all under the square root, of course. So that is all there is to it. So going through into an example or two examples. First one, very simple. It's 6 plus 8i. So therefore, we're 6 on the real axis. Let's say 6 is over there. And we're 8 on the imaginary axis. So let's say 8 somewhere up there. So our complex number's over there. Draw a line from there to the what was the origin, and then therefore this could be a right angled triangle with a length of the base of 6, a height of 8, and therefore the modulus of it is simply going to be the square root of 6 squared plus 8 squared. And then you just calculate what that's going to be. In this case, of course, that very simply comes to 10. So it had a very nice, satisfyingly nice modulus in this case. For part B, we're of course sometimes going to have to deal with ones like part B where there's minuses involved. How does that affect the calculation? Well, not really actually that much. If we have 5 minus 7i, that would be 5 across and then 7 down, because the minus, the negative imaginary component denotes that we're going down on the imaginary axis. So we're talking about a number that's somewhere down here. But again, all we're just interested in is the length. We don't care where this line has been drawn. So the fact it's down here now doesn't really change the calculation that much. You do have a couple of options, though, how you then deal with that minus sign when it comes to the plugging into Pythagoras. You can either completely ignore the minus sign and just view it as the fact it's got a length of 7 when we're talking about the height, and therefore do 5 squared plus 7 squared, all square rooted. But alternatively, you can take account of the minus. Just be really careful to make sure you're putting the minus number in brackets before you square it to ensure that you don't end up accidentally taking away something you shouldn't. In this case, that will end up giving us 25 plus 49 all square rooted, which is the square root of 74. And unfortunately, that doesn't come to a very nice number. So, of course, in pure maths, sometimes we like to leave things in exact form. And so it's okay to do that here, just leave it in terms of the square root. Of course, as well, if it is something that can be put in surd form, do that, because, the simpler things are, the better. But of course, often your calculator will put things in surd form for you automatically. So that shouldn't be too much of a problem. So that is all it is that's all there is to finding the modulus. What about finding the argument of a complex number? Well, first things first, again, notation. Argument is represented by using the letters A, R, and G with some brackets around it of your complex number. So if you're just saying the Z, if you don't know what it is, it's algebra, arg Z. Or if you know the number, you can start doing that around an actual number, like again, 4 plus 6i, let's say. But then what does that mean? What are we actually finding if we're finding an argument? Well, if you have a complex number, let's say one that's over here, again, as usual on the Argand diagram, we draw a line from there to the center. And then the argument is going to be specifically the angle that line has made with specifically the positive real axis. So that's just that right hand side, that half of the real axis. So for our complex number, that of course will be this angle here. However, there's some more details we need to watch out for when calculating it. One of which is that any angle measured anti-clockwise will give a positive value for the argument. So as our complex number is above the real axis. Therefore, we'd be measuring it from the real axis, and we've gone anti-clockwise to get to our line. That particular complex number will have a positive argument. Whereas if we have one down here, then as we have to get from the real axis to our line by going anti-clockwise, therefore this would be a negative argument. So that's something to be aware of. Another thing to be aware of is being an angle. Of course, in maths A level, there's lots of different ways of measuring angles, but for arguments, they are always only measured in radians. So watch out, no degrees for this stuff. And then lastly, of course, we're talking about angles, and angles can go round and around. Where do we stop? Well, generally, often we will write arguments between pi and minus pi, and that's just because that provides the most efficient way to get to any line from the positive real axis. So we're either going to go this way to get around to anywhere around there, or we're going to go around from here to here. And of course, anywhere on the negative real axis will have a argument of negative pi. However, it's worth pointing out that's just a convention. It's not a set mathematical rule that has to be followed at all times. So we sometimes won't do it between minus pi and pi. Sometimes we'll go between, 0 and 2 pi or something else. So there is no set rule that has to be that. So do adapt depending on what question it is you're dealing with. Let's do some examples. So first of all, arg of 4 plus 5i. Well, of course, that's got a real, positive real component. So that's 4 there. It's got a magic component 5. Let's say that's about there. And so therefore, the angle we are wanting to calculate, if we're trying to find the argument, is this angle here. How are you going to find it? Well, use a similar strategy at first to what we did with the modulus. You can form a right-angled triangle. And the reason that's useful is because it then means we can use simple SOHCAHTOA trig or right-angled triangle trigonometry, whatever you want to call it, to find our angle, because we know the opposite of our triangle is 5. We know the adjacent is 4 in length, so therefore it's just going to be arctan that can be used to help us find what that angle is. So arctan of opposite over adjacent, 5 over 4. Type that into the calculator and you will get an answer of 0.896 to 3 significant figures. And therefore, that is the argument done. This time it didn't come out as a particularly nice number. Sometimes it will, because some angles, of course, in radians come out as a nice multiple of pi. So if they do come out in the exact form, of course, it's nice if you do use it. But sometimes you will have to write it as a decimal, or failing that, write it in terms of arctan. However, be careful with arctan. Don't just assume that arctan is just instantly going to give you the full answer. Let's look at arg of 7 minus 7i. That's going to have a real component of 7, imaginary component of minus 7, so it's a number down here. And so what angle are we going to be trying to find? Well, the simple one to find would be to just say, let's find that angle there. However, how we approach finding that angle and how we give our final answer can vary. My personal preference is to draw the right angle triangle as normal. Sorry, that doesn't quite connect up in a nice way. And to realize, therefore, we can treat the sides of the triangle just like length. So I'm going to ignore the fact this is a minus 7 for the height. I'm just going to treat it like 7. So therefore, I'm going to do arctan of 7 for the height over the adjacent, the white base, being 7 as well. And if you type that into a calculator, you will get pi over 4. However, watch out. Our angle to get from the real axis to our line, we've had to go clockwise. And as we've had to go clockwise, you might remember I just said that the argument would have to therefore be negative. So that's something to be aware of. So therefore, it's a really good idea to draw a diagram when finding an argument, because that can help you visualize and work out, have we gone clockwise to get to our argument, or have we had to go anti-clockwise to get our angle? Now, some people admittedly do like to do this a slightly different way. Instead of dealing with the minus at the end by looking at the diagram, they like to include it inside when doing the calculation with arctan. And for B, that will work. So we could use the opposite. Instead of treating it as a length and just treating it as 7, we could use the original number of minus 7. And then therefore do minus 7 divided by the adjacent, which was still a positive number of 7. And therefore, if you type that into your calculator, you will still get minus pi over 4. However, personally, I would say I don't like doing it this way. And the reason for that is students who do this will often get complacent. They'll think that if we'll just whack the minus sign inside the arctan, arctan will do it all with it for me and it will all work out fine. And if it's meant to be a minus, arctan will tell me it's a minus. And if the final answer is meant to be positive, arctan will come out as positive. But that is not true. It did work for this one, but it won't always work. So therefore, I don't like to do it that way. And instead, I like to do it this way. Well, I say this way. I already showed you how I did it for the other one. But also, let's look at some more complicated examples to see how we deal with them. Okay, so part C, arg of minus 2 plus 2 root 3i. That would be minus 2, so 2 over here, let's say, is over there. And 2 root 3, let's say that's up there somewhere. 2 root 3i. Okay, so we want the angle it makes with the positive real axis. The positive real axis, though, is over here. Watch out. That means, therefore, the angle we're going to be finding is this angle all the way over there. However, trying to find that might be a bit of a pain. So instead, we're going to simplify the problem temporarily. We're going to temporarily work out what this angle here is. That won't be the final argument, but it will help us work out what we need. So I'm going to form the right angle triangle. To work out that angle, I'm going to do what I did last time, which is to temporarily ignore the fact there was minus signs involved, because I'm going to have to deal with them later anyway. So rather than trying to be too clever for myself, just think about what the angle is by treating it as a triangle for the moment. So the opposite, is 2 root 3. The adjacent is 2. And so we'd work out what arctan of 2 root 3 over 2 is. However, it's at this point we realize this is the angle we've worked out. That's not the angle I want, though. This is the angle I want. And so therefore, I realize that the angle I want is pi radians minus the angle I've calculated. So therefore, the final answer will be pi minus arctan of 2 root 3 over 2. If you type that in, you'll get an answer of 2 pi over 3. Cool. And so therefore we'll have what we need. Cool. However, something I would add is that, just a general tip, would be to always draw, therefore, a diagram. You can already see with this one, it really makes a big difference to know what sort of argument I should be doing, what I should be doing with the triangle, all that sort of stuff, as well as pointing out to you, if you had tried taking account of the minus sign that's in front of the 2 inside the arctan stuff, you would have got the wrong answer. If you had done arctan of 2 root 3 over minus 2, you would have ended up getting minus pi over 3 as your answer, which we can see is clearly wrong, because a negative argument would be, you'd be expecting it to be below the real axis. So therefore, that shows the pitfalls of doing it that way. And then also worth pointing out, as I said, that the only reason we knew to take pi away from the arctan is because we drew the diagram to go, okay, we've got this triangle, okay, that's good, we got that angle, but that's not the angle we want, and all of that. So please do draw a diagram for all of these questions. Draw a diagram. There you go. Messily written note to you to remind you. Anyway, let's have a go at doing the last one, because that'll give us even more practice at doing this. So arg of minus 3 minus I. So minus 3 would be, I don't know, roughly there, let's say. And then minus I, let's say that's over there. So minus 1 on the imaginary axis. Once again, though, we've got to be careful, though, of what argument of that complex number would be, because the angle, again, is always measured from the real, positive real axis. So therefore, if we're picking the smallest angle we can do to do that, that would be this angle here. However, in order to do that, I have done, of course, a clockwise angle, so we already know that we're expecting a negative argument. But again, we also have to be extra careful, because when we are calculating it, that might not be the angle we immediately get, because I might choose to use this right angle triangle I've just drawn, and then therefore realize that I'm calculating this angle. And that angle would, of course, be arctan of the opposite, which this time is 1. I know it's minus 1, but again, as I said, I don't like to include the minus sign inside. Treat it as a length, and then the base has a length of root 3. Again, it's technically minus root 3, but I'm not going to include the minus, because again, you get complacent if you try and assume the minus sign's been accounted for already. That will come to pi over 6, but of course that's not our final answer, because of course we want this angle here, and therefore we can see we have calculated the wrong one, so we've got to do pi minus our angle to calculate the actual angle we want. But then that alone will also not get us the correct final answer, because, as I said, we know it's been measured clockwise, so it should be a negative final answer. So if you're doing in the working, I just like to put brackets around everything, put the minus in front there, or you can do the calculation and then just remember to adjust with the minus sign at the end. But basically what we will end up getting is this. That will simplify then to, therefore, this. So therefore the arg of minus root 3 minus I is minus 5 pi over 6. Cool. There you go. That's how you find arguments. They are just angles. All you got to do, draw a diagram, I'm going to say one last time, to help you make sure you're getting the correct one, as well as also remember the key skills we pointed out earlier. All these little details about arguments to watch out for. And of course, we also covered what a modulus is. Okay, thank you for watching, and see you in a future video.